Hi everyone, and welcome to another episode of Mr. Carlson's Lab. Today we're going to electrically repair and restore a very interesting instrument amplifier, or guitar amplifier if you like. It's a model K550, a really unique design, two completely separate Class A amplifiers in one case to give you some very interesting effects, and I'll explain that as we're going through the video. I'm also going to share many electronic troubleshooting hints and tips all the way throughout this video. So I guess you could say this video is sprinkled with all of these little hints and tips all the way through. So if you're interested in repairing amplifiers of any sort, definitely watch this entire video. I'm sharing lots of information that's not shared anywhere else. Let's get started. Here's the K550 amplifier that we're going to be working on. And as you can see, the case of it looks fantastic, and that's because it was just redone. So this looked really bad. I really wish I had a picture of this before it actually got redone. It looked like it was dragged behind a truck for a fair ways. It was looking really bad. Somebody had a piece of carpet and they stapled the carpet onto the front. It was just, you can't even imagine. So the fella that did this job, put the new covering on this, did just an absolutely wonderful job, even putting the little piping in here and everything. And then he put the little corners on so that, it doesn't get damaged in transport. Just, it looks fantastic. I can't even tell you how much better this looks. So the case is done, and the amplifier itself that's inside wasn't touched, so it was just carefully removed. The case was redone, and then the amplifier and basically all the innards was just put back inside, and now it's my turn to get inside this thing and make it perform properly. So as you can see, the amp looks pretty rough, and you can see some pretty scary looking wiring down in the bottom here. You can see if we look at the cord, this is, here in focus there. You can see that the cord's looking pretty bad, and it's pretty rigid feeling, so you got to get rid of that. What's going on inside here is very scary looking, bare wires all over the place, things like that. So I really don't know what was going on with the previous owner to the previous owner, I guess. What they had done to it, it's looking pretty bad. So what we're going to do is go inside this thing and restore this thing electrically. I'll clean this up a little bit, and externally, the amplifier itself. The owner of the amp wants the patina left behind, so I'll leave the patina behind, and we'll just clean this up, make it look as good as possible, and of course, make it work electrically like new. And then that's my job. So what I'm going to do is I'll get the cover off of this. I just have to take these screws out here. I'll take this out and I'll slide the amp out and take the speakers out and everything, and I'll get this on a bench where we can take a close look at exactly what's ahead of us. As you can see, it's looking pretty rough. Even the switch, look at this. So it starts to click at about that area, and there's a bit of, as you can see, a little bit of play there. And then it's over there. So it's a heavy usage unit, let's put it that way. So it'll need quite a bit of work. Let's bring this thing back to life and make it perform like new. Here's a quick look at what we're up against. So you can see with the cover removed on the back, it's looking pretty scary in here. So what's happening is you can see that they've run the high voltage leads from the actual chassis, from the output tubes right down to a transformer that's mounted on the speaker itself. And there is no plug. So technically, when you want to service this thing, what you're supposed to do is take the chassis and the speakers all out at the same time. You can remove the reverberation tank here just by unplugging this, but everything else is supposed to come out together. So in order for, I guess, people in the past to service this, what they've done is they've just cut these leads that run to the audio output transformers and taken the chassis out on its own, which is kind of silly because in order to test the amplifier, you need the speakers attached anyways. So you may as well just take it all out as one. But at any rate, it looks like this thing here, has definitely been taken in and out. So I'm pretty sure we're going to be in for some surprises underneath here too. You can see somebody in the past has taped the winding up on this transformer. They've taped it up really tight. So there's a good chance that either somebody has ripped the actual wires right out of the paper on the transformer, or another scenario that I see often is the transformers, they become intermittent. So what they do is they wind them really tight and it makes connection again inside. So this transformer could be unreliable. And of course, if this thing's ever going to be used on the road or anything like that, there can be, no unreliability in this thing. So it has to be very reliable. So I'm going to have to find a replacement transformer for this. And I'm going to look around through my transformer stash. I might have an exact replacement. So I've got a lot of transformers. So I'll go and look through my stash and maybe I can find something that'll match this, put this back in here again, get rid of that ugly thing. So this is very unsafe to have this open like this. These are B+ lines, right? It's high voltage on this, created by this transformer, rectified by this tube, and, of course we have lots of high voltage DC on there, so scary stuff. So that all has to be taken care of along with this, pretty hideous looking line cord. Here's a closer look at the speakers. So everything is removed from the cabinet now, and as you can see, this is looking pretty scary. The speaker itself is in fantastic condition. So just the transformer needs to be replaced, and ta-da, look at that. So I have pretty much an exact replacement in my stock. So I'll replace that horrible looking transformer. The only thing that's different is the windings are just put the other way, so the wires are on the top and then the speaker leads are on the bottom. Now, if I was, really diligent, I could take the core out and then move things around and do all that. But you know what? It's an older transformer, and I really don't want to take the chance at, just damaging the windings, right? Getting frail by now. So I'll just leave the things the way they are, and the wires will just come out this way, and then I'll just run these wires down to the terminals over here, just like that. So very nice that I had that in stock. So this will get replaced. And the other speaker is right here. Everything is looking okay with this one as well. This here drives the reverb. So it's a really interesting design. It's actually two separate audio amplifiers in one guitar amplifier. It's a really interesting little design that they've done. And I'll talk a little bit more about that. And I think that's what sets this little guy apart from the rest of these, little amplifiers that are built like this, and actually has two separate audio sections in it. It's bizarre. So neat system. So I can see why these things have a little bit of a following. Speaker on this is pretty much perfect as well, as you can see. Just dusty and dirty, no problems there at all. So it's nice that there's no holes. Nothing's been poked in these things or anything like that. So and clean these up very carefully. Whenever you're restripping the wires on something like this, what you want to do is hold this with a pair of pliers very steady, and then what you do is you take your clippers or whatever and just gently cut through the insulation and then work against the pliers, so you never pull on these, because if you do, you'll end up like that. So you got to be very, very careful. Never ever pull on these wires. This paper is, very, very thin by now, right? And it is frail, so any type of tugging and you could absolutely destroy the transformer, pull a winding out. So thankfully, this one has, still the same. I notice the magnets are different sizes as well, because this speaker here is the reverb speaker, and this is the regular guitar amp speaker. And a lot of people, they want to get in there and they want to completely change everything out in the amplifier, and they pretty much take their design and make it into their own. So we just want to get rid of the parts that are going to cause any issues in the future, and we want to leave the character the same. And when I talk about character, there's something in this amp that will really give it character, and I'll show you that here in a little bit, and I'll explain why it gives it that character. And it has to do with the capacitors. So this is something that you may not know. So there's going to be a little bit more capacitor knowledge passed down here. So this is the Reverb unit, and as you can see, it's intact. Hammond Organ Company, so they're obviously using these from the Hammond Organ Company. Everything is looking good, no problems here whatsoever. Everything's suspended fully and still working. So we should get our springy reverb type of action. Here's the chassis of the amplifier. And it's a pretty simple chassis. It's just a piece of bent steel, and it's punched with a bunch of holes to put tube sockets and potentiometers and jacks and all sorts of stuff here. So I'm going to have to clean this up. I got to be very careful because this is screen printed on here, and I don't want to take any of this off. So I'll clean this up as nice as I can, and of course, very gently and just be very careful with this because this stuff will come off very, very easy. On the top side here, we have the tubes and the tube sockets. Again, more screen printing. You can actually feel that paint. You're gonna have to be very careful with that. Very simple design, 2 audio amplifiers on one chassis. We'll take a look at the schematic here, which will help explain that to you a little bit more. On the bottom side, it doesn't really look like it's been touched. So I'll zoom on into this just a little bit here. So first of all, there's a line cord that's coming in over here. It's a 2-wire cord that is non-polarized. We have what's known sometimes as the death capacitor, so there is no safety ground or no earth on the line cord, and that'll definitely need to be added to this. So what happens is this capacitor here shorts out or leaks very bad, and it connects one portion of the line directly to the chassis, and this is why guitar players get zapped off these old amps so bad all the time. This is the problem right here. That's the little fella that makes things very miserable. So depending on how these things short or decay, and usually they're very, very bad. We'll test this one here in a little bit to get an idea of how bad past guitar amplifiers may have been getting whacked by this thing. So we'll take a look at that here very shortly. At any rate, this has got to go. We'll replace that with a proper safety capacitor. And of course, again, this will have a 3-wire cord on it, so it'll make it very safe, right? So X1, Y2 rated capacitor is what you want to replace something like that with in many, many cases. So moving straight along here, another thing that needs to be taken care of is, since this is a 2-wire cord, so these are both of the wires that come from this non-polarized cord. So the hot lead of the cord for maximum safety should go to the fuse, the very first thing in line, and everything is after the fuse. So the switch, this capacitor, everything is after that. So if anything goes wrong, the very first thing in line to go is the fuse to protect you and the amplifier and everything else. So that'll have to be changed because one portion of the line cord runs into the fuse and then goes directly into the transformer, and then the other portion of the line cord runs up to the switch and then into the transformer. No, it runs from the line cord to the fuse, through the fuse to the switch, into the transformer, and then the neutral lead goes directly into the transformer and does not get broken. So lots of safety things that need to be taken care of in this amplifier, and that gives you about the maximum safety you can. There is a reason that they run the neutral lead onto the back side of the switch in many of these applications, especially in high gain, is because depending on which way you plug in the cord, sometimes the actual switch, since it's on the back side of a potentiometer, will induce hum. So in this case, this isn't in a very sensitive area, so it's absolutely fine to get rid of that and just make things a whole lot safer. So you can see on this side here, it's just a tone control, and the tone control on this is very rudimentary. Moving straight along here, rectifier tube, we have a capacitor here that is going to get replaced. Another capacitor here, this is doing the filtering that takes the hum out of this entire amplifier. So this is what's cleaning everything up. And it will also stop one stage from seeing another. And that's depending on where you put the capacitor in the B+ line to the plates. Okay. So in a feedback situation, having that capacitor in the right place is very important because that's, again, stops one stage from seeing another stage. When I'm replacing this capacitor here, I'm not going to restuff a can and put a can on here. I'm going to leave the capacitor here for aesthetic reasons. So from the bottom side, it'll look like everything's normal, but all the capacitors will be inside here on a terminal tie strip, and that makes them very easily replaceable in the future. It keeps the capacitor away from the heat of the actual plate of this tube here. When these tubes are in service and they're drawing current, which in this case, both of these are Class A amplifiers in this, so it doesn't make a whole lot of power, and of course, taking a look at the audio output transformer size, we're in about 5 watts maximum, something like that, per, audio output transformer here, okay? When these are running in Class A, and of course you have a vacuum tube, which is a 6V6 right beside it, this tube gets as hot as the blazes of hell. And this is going to obviously heat this capacitor, and so will the rectifier tube. The rectifier tube also gets very, very hot. So we have these two tubes that are upside down, and the heat from the tube is radiating onto the chassis and kind of going around the chassis. So in an amplifier like this, the term you use is convection cooling. And that's how these tubes are cooling. What happens is the heat rises, okay, and it's going to basically flow around the chassis or around in the box, and it's going to draw cool air from the underside, okay? That term, again, is convection cooling. There's no forced air or anything in like this. And if the heat is rising, where's that heat circulating? Well, right around this capacitor where this nice color variation is. And there's actually a bulge on the other side of it. I don't know if I can give you an example of that bulge in the capacitor. I can feel it, but I don't know if I can show that. Let's see if I can show that. There's a bulge right here. I'd probably have to put a ruler across that in order to show you that, but there is a nice little bulge right there. Right? Interesting how it's so close to the tube. Right? So these capacitors, they bake in a situation like this. So if you have the opportunity to leave the old cap in just for aesthetic reasons, and then move the new capacitors onto the bottom side of the chassis, it's a win-win in so many situations. Reason being, you're getting the caps away from the heat. They're very easily serviceable here in the future. You don't have to take a can off or, de-stuff a restuffed can. Putting the new caps in a can like this is you're putting them in a little oven. Why would you do that, right? So that's not going to take any of the character of the amplifier away whatsoever. It's just going to benefit you or the owner in the future. So I'll demonstrate that. I'll show you when this is all done how that's going to look. If there is a red spot on the plate of the vacuum tube, that means that the bias point of the tube has changed, and it's very destructive for the tube. Now, because I'm a radio fella and I know about 807 vacuum tubes, there's a little saying that went around way back when is an 807 doesn't sound good unless there's a little bit of red glow on the plate. Now I have to attest to this, that is very true. Having a little bit of red glow on the plate of an 807 sure does make it sound nice in audio service. But any type of a red glow in a plate like this is a very small plate structure in this tube, is not good. That's indicating a failing capacitor. So with these caps, you don't even take, not this one here, but with these caps here, you don't even take the chance. Anything that's an old wax capacitor like that needs to go. If you don't replace them, it's going to burn your amp up, or it'll burn out an audio output transformer. And who knows, maybe the reason that other transformer's taped up is because it's, I don't know, I guess you could say charbroiling the windings inside it. Who knows? And they might have taped it together to make connection again. I don't know. So at any rate, these are just gone. There's no point in even fooling with that. These are disc capacitors, all right, ceramic capacitors. They have a Z5U rating, so they're about as drifty can get. And when I mean that, you can look at these things sideways and they'll change capacitance value. I'm not kidding. Z5U, these things are all over the map. But it's what gives this amplifier character. And I don't want to change these because if I change the capacitors, it's going to remove a little feature that this amplifier may give to the player, to the actual musician that's using that, and that's called microphonic. These capacitors here are terribly microphonic. I have a video showing how microphonic these are, and what I'm going to do is I'm going to link that video just below this video under the Show More tab. I demonstrate that. I actually have these attached to an oscilloscope, and I tap them, and you can see on an oscilloscope how terribly microphonic these things are. When I say microphonic, they act like little microphones. Okay? Now, that has nothing to do with the Z5U rating. The Z5U rating basically means that the capacitance tolerance and the temperature stability of these things is not super tight. These are great for bypass application in RF service. Absolutely fine for that. In fact, I prefer ceramic capacitors in a bypass application. They're using these things here in the audio circuit. So in the front end of these things, depending on the sensitivity and how the front end of the audio circuitry is designed in a guitar amplifier or in any type of amplifier that has these capacitors will tell you how microphonic or how much of an effect you would get from those disc capacitors in the amplifier. Now, depending on how loud this is played or in what type of a noisy atmosphere, this is going to actually act as a bit of a pickup, and it's going to insert some of that into the audio chain. So it's going to give you an effect that may be desirable to somebody that likes the K550 design. If I was to take these discs out and replace them with a poly capacitor, it would completely eliminate or very, very greatly reduce that effect. Again, taking away from the personality of this amplifier. Every one of these amplifiers has its own personality, and that's put into this by the designer. So that would be very, very desirable. So any of you out there that like the K550 amplifier, that is a very, very strong reason that you like this amplifier, and you may not even know it. These capacitors, disc capacitors, very rarely fail. When they do fail, they fail. They turn into jumpers just like all the rest of them, but they very rarely fail because it's a ceramic plate in basically between, or a ceramic disc, between two plates on either side. There's not a whole lot to go wrong with these things. These very rarely fail, and they very rarely leak. Now you can test them because, just to be sure, I've seen ceramics fail, but very, very rarely. In fact, I've seen them fail in test equipment before. But very rarely in an application like this do they ever go bad. They have very interesting dielectric properties as well that you may not know about. And I'm going to display that in this video. I'm going to share some more capacitor knowledge with all of you. So if you're interested in this, definitely hang around because you're going to see something that you may not have seen before. So they have a very interesting dielectric property, which is different than the poly capacitors or even paper capacitors that are in here. I'm going to put polys in here. I'm going to replace these with polys, which shouldn't change the character other than, what it's doing right now, which is probably destroying itself. So I'm going to replace these with polys, and they look somewhat the same. They're a yellow capacitor, and I will also research the outside foil end and put these the right way around, just like these are. And I will also give you a demonstration. I'll open an end of one of these things, and I'll show you what I mean by temperature stability and what I mean by the dielectric properties. In fact, I can probably skip the temperature stability. I'll just link in that other video below. You can go check it out there. But I'll demonstrate the dielectric, I guess you could call it, interesting property that you may not know about these. And this is pretty much something that isn't even talked about. So one of the little secrets that gives these amplifiers their character. Over here, you can see they have a whole bunch of resistors, and, they're all over the place, but you can see that these resistors, a little cluster of them, 22K resistors over here, they don't have any fourth band, which means that these are 22% or 20% tolerance, 22K resistors, 20% tolerance. You can see that they're kind of a squared off type of resistor, which means that it's an early Allen Bradley style. These are very good usually, even though they're within 20% tolerance. The designer of the amplifier figured that they didn't need to be any tighter than that, so if they all test good, we'll leave them in. Whereas down here, you can see that we have some very small, roundy style resistors down here. They're much thinner than these ones. They have a gold band on one end, so this is 2, 7, and 4 zeros, that's 270 K ohms at 5% tolerance. Now, roundies are very bad for moisture ingression. All right, so they let moisture into the case inside, right? And it affects the plug. So they have a carbon plug in the center of them, and the leads are going into each end of the carbon plug. And that carbon plug will change in value if it has moisture ingression. Well, do you think that this amplifier has any moisture ingression? I would say so. So chances are these resistors, if they're not noisy now, or if they haven't changed in value, are definitely going to get noisy and change in value. These will have to go hands down. These will be replaced with another resistor of the same value that will resist moisture ingression. Again, Carbon resistors, changing these out with a different style of resistor again, may change the personality of the amplifier. So for any of you that have done any experimentation and compared a carbon resistor to a metal film resistor, to a carbon film resistor, to a wire wound resistor, will all know that they act differently under temperature and under load conditions. There's a reason that when you take apart an old CRT monitor, they're full of modern resistors, and then right by the flyback, they'll have one of these style resistors. Have you noticed that? Again, I'll get into talking more about the differences in resistors and what they actually do and how they'll affect things in the future. One of the big things is inductance. These resistors are very, very non-inductive. Now, when you talk about inductiveness, if you guys are, for all of you engineer types that are watching here, I'm going to tell you, of course, the lead itself will act as an inductor at a certain frequency, but for most of the frequencies that something of this size can operate at, it's going to ignore the lead. The very first thing that I'm going to do is remove everything from the chassis. Reason being is electricity and rust don't play nice together. Now what they've done when they've assembled this is they've riveted the tube socket retainer rings to the chassis, so I have to drill out all of those rivets. Now in order to create an effective ground system here that would, I guess you could say, moderate any type of noise to keep the static down, is they've run a ground from the eyelet of the actual tube retainer ring all over, it basically just chases through the amplifier, runs up from this one here to all of the jacks and everything like that. They've even connected the cases of the potentiometers to a ground or to a shield to try and keep everything quiet. As you can see, they really haven't cleaned the paint off or anything underneath any of these parts. Now this is done in the assembly process just to make things quick, right? So what I'm going to do is remove everything from here. It's just, going to be a little bit labor intensive. Even the transformer, everything, I have to desolder wires, remove this capacitor, which requires removing all the wires from the cap, drilling the rivets, twisting the actual locking lugs straight so I can take it out of the retainer, and then the retainer will come off from the bottom for this capacitor. And the actual tube sockets and the wiring and the VRs and everything can just basically lift out. It'll kind of just look like all the tube sockets are stuck in one spot and it'll drop into place again. And by doing that, I can sandblast the inside of this rusty area. The face of this isn't bad at all. It's just down here's a little bit here, not a big deal. It can be just taken care of with some rust paint. There's no connection here, some rust inhibiting paint. But this here really needs to be clean. So I'm going to sandblast this and I'm going to repaint this. And I'll repaint it a flat black color. And then what I'll do is I'll put the tube sockets all back in, mount them in with screws, and I'll clean off an area by each tube socket retainer ring, and I'm going to directly solder each retainer ring directly to the chassis. Now you'll see on this portion of the chassis over here that this rivet here is a grounding area, right? You can see over here they also have a rivet here, and it's a ground, and as you can see, that could become a very flaky type of ground. Right, there is no actual solder to the chassis. This is a metal chassis, it's not aluminum, so it will solder nicely. And you can just see, like, there's, a lot of things that could be taken care of to make the amplifier just all that much better. Now, this kind of operation does not take away from the tube amp's character or sound or anything. It's just going to make things better. Nobody wants to hear hum or static or crackling in their amplifier, especially, after a bunch of time when things are corroding underneath these tube socket retainer rings, right? So that'll just make the entire amplifier way more solid. It'll get rid of all of this, rust that's everywhere in the chassis here and make the amplifier just all that much nicer, and it'll last the term down the road, right? Now, if we look at the face here, you can see I just polished this one area just briefly, and as you can see, it looks so much better than this. So this came out pretty nice. And while this is, completely, stripped down, basically, what I'm going to do is I'll go over this and clean the whole thing up. So I'll show you this. What I'll do is I'll get this all cleaned up and, I'll sandblast this and I'll show you the steps here. I'll be right back. Transformers removed, fuse holders removed, capacitor, knobs, all the hardware is screwed back on, all the rivets are drilled out everywhere and pulled back through, and then we can do this. So now I'm down to the bare metal here, aside from this, whatever that's put there for. That looks like that's been there forever. It's pretty clean under that. So now what I need to do is just get the remainder of the rivets out here. I get all of them out, and then I'll end up sandblasting this, and when it's sandblasted, I'll be back. And this is what it looks like after it has been sandblasted. So what I'm going to do now is paint this flat black. I need to get this done very fast because when you take the paint off steel and after you sandblast a piece of steel like this, it tends to rust very, very fast. So I need to get this painted very, very quickly. So what I'll do is I'll end up painting this, and then what I'll do is anywhere where I need to solder to this, what I'll do is I'll just scrape the flat black paint off, and I'll be left with this. It's just that clean. And this, when it's taken down to the steel like this solders wonderfully. So that'll work out very, very well. So everything will have a nice, clean, solid ground after this, and that'll keep the amplifier nice and quiet. So I'll get that done, and I'll be right back. The steel's been painted flat black, and it turned out very well. Pardon the dust. The dust settles on this. It's been sitting on the bench for a little bit. So, worked out very well. Nice clean steel under this, so I can carve away at this, and where I want to solder the retaining ring for the tube sockets, it'll make a nice solid connection, and it will work very well. And I'm also going to clean up the face and the rest of it now too. I want to get that done before I mount everything back onto the framework here. So I'll get all that done, and we'll start putting this thing back together and make it work like new. A little bit of Vim, a product that I use to clean, and a little bit of car wax, and it didn't come out too bad. So it's actually looking pretty nice. The entire face came out. There's some spots here that show its age and give it character, and of course, it's just the paint the way it is from way back when. But it turned out very, very well. So I've got some wax on stuff here. That's the reason it's looking like this here. I got my gloves on still and everything, but at any rate, now I can start putting the circuitry back in and making this thing perform like it once did, if not better. I've spent some time cleaning the wiring harnesses and all the tube sockets and everything like that, brushing off the resistors, cleaning them right up. And everything came out really, really nice, as you can see here. So now I use a product to clean this. Now I'm not sponsored by this company in any way, shape, or form. I just found that it's a product that works very well, so I'll share it with you. It's a product called Mean Green, and I believe it's extra strength or super strength or something like that. And I just spray it on the wiring and the tube sockets and everything and just let it sit. I'm very careful not to get any of it on the potentiometers and any type of a movable part or anything with a moving carbon track inside, just because, this is a more sensitive type of component, so I want to keep all of that out of there. But everything else got hosed down with it, and it works so well you can pretty much just let it sit for a moment and then rinse it off, and it'll come out like this. Now I fine-tuned everything at a toothbrush, and I just kind of went over everything just to make sure everything is nice and spotless. You can see it even put a shine on the wires. So that worked out very, very well, and this is ready to go back in. Oh, after I did that and everything's still wet, I take it out and use an air compressor and blow everything off, blow all the water off. And I pre-lubricate the variable resistors, so I clean them and lubricate them before I put them back in, and that's every single one. And the switch, there's a nice little hole here that gives a little bit of lubrication access to the switch inside. So I gave that a shot of lubricant there. And of course, when I do that, you got to move the VRs back and forth a whole bunch of times because you want that lubricant to get on the carbon track. After you use a cleaner, usually what that does is that washes out all the lubricants, and then you have a carbon track with just a wiper on it, and they'll wear really quickly. So what you want to do is you want to make sure that you have I guess you could say a tested lubricant that you can put inside of a VR to make sure that everything is safe so that it doesn't wear the carbon track. Now, I've spent a lot of time researching that, and I have an entire dedicated video on Patreon about this stuff, about cleaning VRs and all sorts of things with some lubricants that I've tried and used myself for a long time, and they seem to work just fantastic. So, at any rate, this is ready to go back in. I'm going to clean everything up here and put it back in. I'm going to look for some different mounting hardware. Some of this, the nuts on these are looking pretty rough, a little bit rusted, things like that. So I'll see if I can find some replacement nuts and things like that just to clean things up. I still have to clean up the knobs. You can see there's, lots of finger goop inside there. Look at that. That's years and years of dirty fingers massaging this thing. So they're all like this. And look at that. So I still have to clean these up before I put them back on. I honestly think that this design would have probably looked better with, you know, a somewhat bone or white colored chicken head knob. I think that would have been maybe a nicer choice, but I believe these are factory for this amp, so they're going to go back on to keep this looking, you know, as close to original and taken care of as possible. Here's just a quick little side note, just admiring the quality of way back when. So this is known as a jewel lamp, and you see these on many of the modern guitar amplifiers, except they're all plastic now. Now this thing's made of metal, and it's heavy, you know, it's got quite a bit of weight to it, and this lens cap threads into the main body, which usually stays in the amp. As you can see, this is threaded in here, and it almost feels like it's glued in. I don't know, maybe somebody, it's just so incredibly tight, I don't want to take any chances, you know, marring this up because it looks so nice, so I just unscrewed it from the backside and carefully removed the whole thing. This is on here incredibly tight. Now the reason this has ribs on it is so that you can get something there to grip it and, you know, and unthread it. Again, I don't want to, you know, wreck this or destroy it. I want to keep this looking as nice as possible. So the easiest route to get it out is the way to do it. At any rate, when you look at this, you can just marvel at the quality behind this, and it's such a nice looking color. So I have a bulb here, and I think I do have a 9-volt battery over here. So let's see if it does work. Look at that. It's meant to be. You know, just look at that. Look at that nice color that this creates. You know, I'd probably wash the camera out a little bit, but you can get an idea of how nice that jewel lamp looks. Now it has dust inside and things like that need to be wiped out, but you know, not a big deal. And just a little side note there. And just the quality behind this stuff is, you know, very impressive. Again, the nowadays version of this is featherweight light, and it's just a piece of plastic. If you were to put an incandescent bulb in one of those things, it'd probably melt it. In fact, I know they melt because I've replaced ones that have melted, whereas the old ones are actually made out of metal. At this point, I have the new line cord installed, so I have a grommet here installed. It's a vinyl grommet, not a rubber grommet. I find that the vinyl grommets don't tend to decay like the rubber ones. Same thing with these. These are both vinyl grommets. Again, the same stuff that I used in the Vitalizer when I was restoring it. Just they last the term, right? There's a 3-wire cord now installed here. There's a longer screw with a bunch of nuts here holding a retainer that holds the line cord in place. So that's absolutely solid in there. So this nylon clip holds the line cord, and the line cord also curves around. There's lots of restraint there. When I put the nylon clip, first of all, is tight enough on the actual line cord, but to be even safer, what I do is I put some super glue on the line cord and I slide it back in to this nylon retainer, and it turns that basically into cement at that point. So you could, you know, whip this thing around in circles by the line cord and this would never even move. So it's tightened right down onto this. Let's get this in here. Tighten right down onto this. So basically there's a screw coming through, there's the washer, and then there's a nut holding the transformer, and then there's another washer on the bottom side of the nylon retainer, another washer on the top, another lock washer, and then the top nut there holding everything together. There is now an earth or safety ground attached to the chassis to here on the tube socket, and it's also attached over here to the transformer. Every tube socket and the capacitor and everything, anything that needs to be grounded to the chassis has a solder connection. So from the retainer ring to the chassis, every tube socket has that. This terminal tie strip, which now houses the new filter capacitors, same thing. So where it fastens down here, it's soldered to this ring, and this ring is soldered to the chassis. This ring was originally a hub for a whole bunch of grounds, so those grounds attach to this same ring again. It's just that this is much better grounded to the chassis now. So the hot lead goes right into the far end of the fuse holder, so this is the end furthest away from the ring. So it's just good practice to do that, have the hot right down at the bottom end of the fuse holder. It comes in there, and that's the very first thing in line. After that, it goes to an XY rated safety capacitor to the chassis. So that's replaced this capacitor here this one right here, which says Mylar on it. So chances are this is going to be a low leakage capacitor anyway. So they were thinking when they put this together. There was quite a bit of thought, and I can tell that engineers did design this, and I'll explain why here in just a bit. So this is a very good cap. So I would imagine this has low leakage. We'll test it just to verify that. I haven't done that. I've just removed everything already. So from the ring portion of the fuse, this runs over here to the switch, and then through the switch into the transformer. The neutral just goes directly right into the transformer. It has some heat shrink on it and runs into the transformer right there. New switch installed over here. The original switch is rated half of what this switch is rated at. And as you can see, nice and solid now. None of that slop in there anymore. So the capacitor that was across here was a cathode capacitor for the 6v6s, so that's been replaced by this capacitor here. Capacitor technology has changed, right? Look at how small that is, and it has way better ratings than the old capacitor. Do I have the old one off the side? Yes, I do. So, you know, old capacitor, new capacitor. Yeah, quite a difference there. So I've replaced that 22K resistor with another one and a brand new 10K ohm resistor here on this terminal tie strip. This would normally have been across the capacitors here, but I've mounted it over here. As you can see, I haven't changed out any components over here because I want to show you a few things before I end up doing that. That's what we're going to do here in a moment. So these here are the coupling caps. I'll do some demonstrations with those, and we'll also test these resistors here, and I'll show you a little trick. And this is a trick that not a lot of people know about, so I'll share that with you here in this video. You'll find that pretty interesting. It requires the use of old test gear because new test gear doesn't do this stuff. So at any rate, I'll show that to you in a moment. The wires are still the same, but been run through new grommets over here. And all the little, this is all dust and dirt that you're seeing on the chassis from me soldering, and, you know, little bits of flux spatter and things like that. That's what that is. So that turned out really nice. Everything went together very nice there. And see on the top side here, without the glare, you can see the tube sockets and retainer rings, and everything has been put back together here with screws. Everything is very nicely put back together. Nice and solid, very solid build now. So this is technically the way it should have been made when it came from the factory. First of all, let's check out the original factory capacitor, which is now unhooked, just because it's getting on in years, and that could be an undependable portion of this amplifier. So it's always a good idea just to put brand new electrolytics in. So I'll put this to ground here, and this is on the electrolytic setting as of now. And let's check out the 40 microfarad section of this capacitor. So 40 and 220s in this, rated at 450 volts. So let's check this out and see what we get. So the red scale is pretty bad. If it's on the red scale, you'll see it switch over here to a yellow scale if it makes it that far. So it's already into the yellow scale. So it's not doing too bad. And as you can see, that 40 microfarad section is fine in the original capacitor. Now, when I click this to discharge, this shows the charge that's in the capacitor now. So it's a good indication that it's holding a charge. You'll see that. There's a pretty good charge in that 40 microfarad section. Let's go over to one of the 20s. Okay, so let's give that a try. No problems with that either. Let's try the other 20. Not bad. So the original filter can would have worked. So it wouldn't have damaged anything in the amplifier, and that would indicate why Most likely none of the resistors were looking like they were incredibly burnt or anything like that. So the actual capacitor here is still testing okay. Again, they can be very unreliable, so it's always, even if they test good, you always want to get rid of those in these older amplifiers. As I said earlier in the video, you know, I could feel a bit of a bulge on the side of the can here, so, you know, some warning signs. So always good to leave these in for just aesthetic reasons so that they look good, and put some very high quality replacement caps. And these are Rubicon capacitors up here, which have extremely good ratings and a very good life. So, okay, so let's see, what else can we test here? Oh, we can test out the old capacitor that went on the cathodes of the 6V6s. We can do that as well. So I'll just hook this up. Just lay this in here, make sure the leads aren't touching anything. Let's stay. Okay, so here we go. Let's test this one out. And this is counting down well as well. So the red scale is a very coarse scale, and then when it flips over to the yellow scale, you're on the final run, and it's a little bit more of a compressed scale, but it's closer to passing. You'll notice that the yellow scale usually moves just a little bit faster, just to give you an idea that, yeah, you're getting close to completing the test. So when testing larger capacitors, having the red scale is very beneficial because it shows you that, yeah, the actual capacitor's taking a charge. You know, if there was no charge being taken and it was just sitting on one red LED, it would just sit there, right? Whereas if it's taking a charge, it will advance. So kind of a nice little feature of this newer capacitor tester here. Okay, so there we go. So that's that. So what else can I show you here? So let's test one of these paper style capacitors here. Okay, so I'll just open this up. I'll just test this. Oh, one of the things that I was going to tell you, that tells me that this was designed by an engineer, is they actually know what the foil side is of a capacitor. They have both of the foil sides, which is indicated by the band. So that's the outside foil, which shields the capacitor right up to this point inside. I may be able to demonstrate that to all of you as well here. So they've installed these both the right way. So this side runs to the plate, so the outside foil portion of the capacitor runs to the lower impedance portion of the circuit, which is the previous plate stage of the amplifiers. So this end runs to the grid, or the input of the output tubes. So these are installed the correct way. So somebody knew what they were doing here. Looking at the chassis and the way it was put together, you know, and you see they've loomed it with black tape and things like that. It makes you think, and the schematic actually for this is hand-drawn, by the way, too. It seems every schematic you can find looks the same, and even the one in the cabinet looks hand-drawn. It's like a hand-drawn schematic, but scanned in, kind of. So it's, yeah, a bizarre thing. So it makes you go, you know, is this kind of amateurish? You know, but, you know, there's a lot of things in here that tell you that, you know, the guys that put this together, or gals, or whoever put this together, did a pretty decent job. You know, it looks pretty good. Okay, so this is one of the coupling caps. So let's attach this. So the sense lead is going to have to go to this end here because I opened that end. Doesn't matter. So the sense lead always has to go to the open end, or you'll be looking at the rest of circuitry and picking up noise and things like that. The sense lead on this is shielded. So just the center conductor comes out to the clip, but it's shielded all the way up to keep noise out of this. This is a very sensitive tester. This will test into the picoamps. Okay, so I'll put this on here. First of all, let's test this as just a paper and poly, and we have the forecast. So this is forecast, and this is the paper and poly setting here. So let's just see what happens, get an idea of what kind of condition this is. Not bad. Go back to forecast. So this is going to be sensitive up to about 40 billion ohms. And as you can see, it's not climbing back up on the forecast position either. So that'd be a really good indication of why I don't see any charcoal briquettes in here, because there's a really good chance that these might be mylar as well. So very unusual. Very, very unusual. Of course, we're not going to take the chance. We're going to replace these things, right? But on the forecast position, this tests fine. Let's test this other one just to see what's going on here, to see if they're actually using a really high-grade capacitor. It's unusual when you see this. Is it written? Oh, there it is. There it is. It's written right there. It's hiding on the other side of the cap. Mylar. So we know that these are going to be good caps. So you have a paper body on them. And I'm going to get rid of them just because of that. So we'll put a newer capacitor with even lower leakage than these in there. Okay, so here, we'll do this. Just clip this on here, onto the forecast position. So at this point here, we're about 5 billion ohms. And as this is counting down, this is counting up to 40 billion ohms. So right now, this is surpassing, once this goes green, this is into the picoamps right now that this is passing. Right now, that, what you see, just a little bit of red in that last lamp, is about 700 picoamps. Okay. So there you go. And of course, that's with the current that this thing is supplying, the voltage and everything like that. Okay. So those are okay. Now here's something very interesting. Okay. I'm going to show you something very interesting about these disc capacitors. And it's going to require a bit of heat to do this too. Okay. Something that you may not know. All right. So I'll attach this. I'm going to leave this on forecast. And I'm just going to put this on here. All right, looks pretty good, right? No problems, right? Yeah, as a disc cap, what would you expect? So I'm just going to heat this a little bit with my fingers. Again, I'll just heat it with my fingers just a touch. So it surpasses 40 billion ohms, okay, in the forecast. When I heat it with my fingers, as you can see, it's like the capacitance in this is changing because these capacitors are so, I guess you could say, sensitive to heat Z5U. They move all over the place. If you were to design a VFO with any Z5U in there, you would need a steering wheel on the front of it to keep the thing on frequency, and you'd have a full-time job. So the capacitance is changing, and of course the capacitance is moving around so much. Some of these things will move up, some of them will move down, depending on the way that they're built. So, and as you can see, like, I mean, once it gets warm, it'll stabilize a little bit, so it won't actually move so much. So what I'll do is I'll just turn on one of my heat tools here, and I'll give you an idea so I'm not touching it, so you know that there's no trickery going on here. So wait till this gets hot. And that's getting pretty hot. Okay, so here we go. Look at that. Now the funny thing is the more I heat this capacitor, the more, I guess you could say, the less sensitive it will be to change in temperature. So if I heat this thing up really hot, now you can see it go down. Now if I put my fingers on this, right, it's pretty warm right now. So if I just touch this with heat, you can see that now that it's warm, it's not moving. All right. Now watch. I'll let this cool down here for a moment. So I can cool it off with my fingers. Sorry about the noise. This tool has a compressor behind it, a little electric compressor, and it gets pretty noisy. Try and cool this off as much as I can. Had a piece of aluminum, I'd sandwich it in between there and cool it off. Okay. See how sensitive that gets again. Whereas if you heat it up, it'll eventually come back down. Now watch. Pretty interesting. I'm actually melting the wax on the capacitor. They have a bit of wax on it. So the capacitance is changing so much that, of course, it needs to... Shut this off. So the capacitance of this capacitor is changing so much, dropping or increasing depending on the type that you have. Some will go the other way when you heat them. So, like negative or positive temperature coefficients, the way that these things are put together. That's where an NPO or NP0 style capacitor is very beneficial in a VFO. But at any rate, you can see that it's changing, right? The capacitance is changing so fast that it makes the meter move around, because now this either is the capacitance all of a sudden is just, I guess you could say, it needs to charge more, because when I'm touching it here, all of a sudden it's getting more capacitance. So this goes, oh, I need to charge it again. And then it comes back down again, and some will go the opposite way. So you get to see a kind of an interesting dielectric absorption capacitance change effect that's going on inside of these ceramic capacitors. It really is kind of interesting to note this kind of stuff. It's very easy to find out what kind of a temperature coefficient your capacitor has. I've got another one here. I'm not sure if this one goes the same way. This one might go the opposite way. I think it may. Okay, so this one is a little bit more capacitance. So if I heat this one up, I think this one might go down. I'll wait till it gets into the finer scale because it's easier to see what's going on here. I'll turn this back on. So it's going down. So if I heat this one up, let's see what happens. Oh, you can see this one goes the opposite way. So you can see we have we have a negative and a positive temperature coefficient between both of these capacitors here. So I'll cool this off. Okay, so I think it's at room temp now. So if I heat this up, see if we heat this up, get it nice and hot, and if I cool it down fast, we might get this one to climb. Okay, whereas that one went the opposite way, right? We can cool this off real quick. Press this against the chassis, cool it off. There it is. And I'll heat it up again. See that? There we go. It's backed up again. So you can see this one moves the opposite way. Kind of an interesting thing to note about these ceramic capacitors. Now, an NP0 capacitor, the capacitance should be very solid. So if we were to put that in here, we would find very little to no movement because the capacitance alone inside isn't going to change. So the properties and the leakage and everything, the properties of the capacitor will be completely different as than something like this. So you can see that these two go in opposite directions. So technically, if you were to trying to create something that would compensate for the other, you could put a bunch of these things together and then have them close to a source so that if one capacitor moves up and the other one moves down, you get somewhat of a stability area in the center. One would compensate, the other way, so you'd compensate with each other. At any rate, just an interesting little side note about ceramic capacitors. All right, let's test some resistors. So let's test this 22K resistor down here first and see what we get. Pretty close for a 20% resistor. Not too bad. Let's test this 1.5K resistor here. 1.56. Not too bad. As you can see, the Allen Bradley style carbon composition resistors, they hold up very well. So these are roundies. And we all know what happens with roundies. So let's test this roundie here. What are we at? So this should be 270K ohms. Yikes. 314. Let's test this one. Again, 270. It should be 270. 275. That's not too bad. Let's see what else can we test here. Again, as I've mentioned before in my other videos, we're dealing with high impedance circuits here, and a lot of these resistors end up at open connections when the tubes aren't in. So, and most of them, well, if the tubes are in, they aren't usually an open connection anyways when they're not powered up, right? Because it's basically a vacuum inside. So vacuum tubes are high impedance devices, and much of the time when you're testing components like this, the nice thing about working on vacuum tube equipment is much of the time you can test the components right in circuit without having to lift the legs off our resistors. Where much of the time in semiconductor gear, you need to lift one leg of the resistor up because it's getting pulled down at some other portion of the circuit and you get a confusing reading. That's kind of one of the nice perks of working on this old vacuum tube stuff. Let's test this. This is a 47K ohm resistor, no fourth band, so it's going to be 20% again. Let's see what we get. 48K. Yes, just no problems. 48.7. Fine. I usually only just go by the first two numbers. We're dealing with tube equipment here, right? Yeah, no problems. So this is a 100K ohm resistor right here. All right. Brown, black, yellow. 104. For those of you with modern speak. Oh, and if you're new to this channel, you'll probably find that I go from microfarad to picofarad. So I'll miss the nanoscale, so you're going to have to be using decimals with me. Because I'm an old timer. 231. 231K ohms. Am I reading the right terminal here? I think I might not be. I'm not. This is the 220 most likely I was just reading, 230, and that's 20%, so no problems there. 94K, that one's going the other way. No problems. So it's all okay. And you know what? These 20% resistors, even if they're even just a little bit over 20, that's going to be just fine for the age. If it's loose enough to have a 20% tolerance resistor, not a big deal. Right? Like these resistors, there's a lot of them are just 20% resistors. We're not dealing with anything that's acting as a voltage regulator or anything with a divider in it or anything where we need accuracy through divider resistance, anything like that. So, you know, this is all fine. Like these are just stoppers. The reason that they have these things here is to stop oscillations. So there's 22K resistor running to the jack on each one of these things. If it's 22K, you could replace this with a 33K. You could even replace it with a 47K resistor. Not a big deal. These are just stoppers. The gain at the front end of this thing is so incredibly high, it almost doesn't even see this, right? But very effective to stop oscillations. What else can we look at here? That's pretty much, you know, everything. We can take a look at this 250 ohm 5 watt resistor. 258, no problems there. Everything is looking really good, you know? So this resistor here is definitely going to be replaced, and so is this one because these are roundies and they're kind of a small body. Now these things tend to get noisy, and they can be tested in a very interesting way, a way that you may not have seen before. So I'm going to share this with you, and I'm also going to show you a way to make them noisy. Let's do that. Let's test this resistor here and see if these old roundies are actually noisy. So hopefully this microphone will pick it up from this distance here. So what I want to do is I want to attach the ground end to the end that's running off to all the B+ lines in the circuit. So they kind of split off of this Y here. So one resistor splits this way and one splits the other way. So let's go to the one that's moved in value. I want to put the ground end, let's move it over here down to the bottom. I want to put the ground end, again, on the end that splits off to all the rest of the wiring in here. And basically, the open circuit end, which, because there's no tube in there right now, and even this capacitor has been removed, I want to put the sense lead onto that, or the audio pickup lead onto this portion right here. So what I'm going to do is I'm going to click the tester to the noise position. Now what this does is this puts current across the resistor. Now usually these old Heathkit signal tracers, they put quite a bit of voltage across that, so you definitely don't want to be touching, you do not want to be touching these leads when you're doing this. You always want to make sure that you click it back to tracer so that there isn't any type of B+ or high voltage on these leads. And this is the way that they listen to noise. So basically what it's doing is it's loading the resistor and it's listening to it at the same time. Really neat feature of this older test gear. All right, so I'll go to noise. I also did a video on the restoration of this as well. If you look in my videos list, you'll find the entire restoration on this and modification and everything like that. So here we go. I'm going to give it maximum gain. Listen. Okay, so I'll go to the other resistor. Just turn this down so we don't have to listen to the huge noise. Let's go to the one that's closer to value. Okay, this one's very close to value. So turn this back up, click it to noise. Not very noisy. This hiss that you hear here is just the incredible amount of gain that this device has. Pretty quiet. Okay, so click this back to tracer. Turn this down. We'll go back to the other resistor, the one that's moved in value. Turn this back up. So if we were to leave this in and give this back to the customer or whoever owns this thing, you would be hearing this in with the guitar playing or whatever instrument you're using to amplify. So now here's the trick. This is a really neat trick. Now we have the ground end of the probe, which is just the BNC here, attached to the rest of the line in here. So of course, you know, this thing is unplugged. There's nothing in it, right? We're just listening to this resistor. So what we're going to do is we're going to touch a soldering iron to the ground end of the probe. Okay, so we're just going to touch this to the ground end of the probe, right to the ground end of the resistor, I should say. So that the soldering iron will just be attached to the ground of this device. I wouldn't want to touch it over here because this is putting B+ on this side of the resistor. Now it's very low current B+, but still, nonetheless, any type of sparking that you get on your soldering iron tip, if you touch something and it sparks just a little bit, that'll take the plating off your soldering iron tip, and if you use your iron enough, in a day or two, you'll have a big hole in your tip. So you don't want to do that, no sparks. So what I'm going to do here is I'm just going to heat one end of the resistor and watch what happens. Now, this is a really neat little trick for those of you that want to verify if the component actually is noisy. Okay, turn this back up. So I'll get my soldering iron and I'm just going to heat this end of the resistor. Okay, I'll touch this to the leg. Hear how noisy that's getting? So, I'll let that cool down. Listen, you can hear it dying down. I'll add a bit of solder to the tip of my iron here so I can get a little bit better thermal conductivity between the iron and the component, and we'll do it again. Alright, so add just a bit of solder here. Okay, now listen very carefully. Now I'll remove my iron. So there you have it. There's a little trick for you. So if you want to verify, always turn this back onto tracer. It's kind of like when you have a DMM and you leave the probes into the current setting. The next time you go and read voltage, you'll pop the fuses in your meter. It's the same kind of idea with this. Whenever you're done with this, always click it back into the tracer position so that you don't give yourself a buzz with these older pieces of equipment. So anyways, there you go. There's a little trick for you to help you verify noisy components. Just heat the ground end lead. And if it is noisy, most of the time, when this is in the noise position, you'll hear it. And as you can hear it, it got very, very bad. So actually, why don't we test this other one? Let's see if it's noisy as well. Okay, this one here was pretty close to value. So this one might be more stable than the other one. Let's just do this for the fun of it. Okay, turn this back up. Click this onto noise. Still have a nice chunk of ugly solder on my lead there. Let's see if this one's noisy too. A little bit, but not too bad. Not too bad at all. I'm now about to replace these capacitors with a modern equivalent. Now the modern equivalent capacitor to this would be 0.047 microfarad, and mine are rated at 630 volts, so they have a better voltage rating than these. I want to replace these even though they say Mylar just because they have a cardboard tube on them. Now I'm not sure if this is another sealed capacitor inside here or not. And down the road, I may actually dissect this, and we'll take a look inside this capacitor. It sure tests nice. It tests very well, even on the forecast position. So it's obviously protected inside there, or this is just not being affected at all by any type of decay over time. Now, this is the new modern capacitor, and these aren't marked for an outside foil end, just because these things are modern capacitors, and most modern capacitors sit on circuit boards. They don't have flying leads. So people aren't producing things nowadays with point-to-point wiring just because of cost, right? It costs a lot of money to do this. This is all hand-built, right? Whereas everything nowadays is put together by a machine. So it doesn't pay the manufacturer to spend the time to mark the outside foil when this is going to sit on a ground plane on a circuit board. So whenever you're using something like this in point-to-point wiring, it's always a good idea to spend the time to find the outside foil end, and that's what this little device does. Now this is another little device that I've invented, put together, and shared on Patreon. Everything is up there. Circuit board layouts and schematics and alignment and everything for this thing is all up there. It shows you how to align it at any rate. It's a very simple circuit to build. All right, so what I'm going to do is attach this to the leads. Now how this works is, you'll see a display up here. I'm looking for the least amount of LEDs lit with the corresponding LED down here. So the least amount of LEDs with, say, this lamp lit would tell me that this is the outside foil end. So if it was the least amount of LEDs with this LED lit, this side would be the foil end. So it's telling me that it's shielding the noise from my body. I am acting as a big antenna for this thing right now, and I'm inducing noise into the capacitor, the same type of noise that you would get in a vacuum tube circuit if this was, say, very close to a heater line or something like that. All right? So what I'm going to do is turn this on, and I'm going to hold this right in the center, and I may have to adjust the sensitivity. Well, it's actually working very well. So you can see that this is the outside foil end. That's the least amount of noise. Lots of noise, least amount of noise. Lots of noise, least amount of noise. Okay. So now what I'll do is I'll take this out of here and I'll just turn this around. Now the effect should flip. Now this should be the outside foil end. Okay, so I'll put this in here. Put this in here and very carefully hold this right in the center. Least amount of noise. Lots of noise. Least amount of noise. So you can see we've flipped it around because we flipped the capacitor around. So I need to mark this end as the outside foil end. So I'll just take my felt, and usually what I do is I just put a little dot right here, just like that. So it's out of focus here. You can see that, just a little dot on the end of the capacitor, and that would be this way because the dot's on this end, and that's the outside foil end. I removed this transformer, so I took a grinder and I ground off the rivets. So these little rivets right here, ground them off very carefully, and then of course transformer just comes off, but the studs are still sticking through the speaker, so I need to get those studs out of there. So I need to give myself a limit stop, and it's nice that they've drilled more holes here for different sized transformers most likely. So all I do is I put the plier in one hole, and then I press the stud of the rivet, and it just kind of pops through and then falls down in. You got to be very careful. You don't want to be pushing down, and you definitely don't want to drill anything like this out, because if you go through the paper. Of course, we want to keep these speakers as flawless as possible because they are pretty much flawless right now. So again, just put the plier through here and then push on the rivet right through, and it gives you a limit stop so you can't get close to the paper, and I can safely remove those studs. Now that this is out of here, and as you can see, it's been completely, they've ripped the wires right out of the transformer, and they're using this tape to hold it here. So definitely a bad situation, that thing. So the new transformer will mount to the same place, just like so. Right up here, like that. And once that's done, I need to check the phasing I need to make sure that I connect this wire to the correct side. It may go to this side or it may go to that side. If I have the speaker wires reversed, when this speaker is pushing, this one will be pulling. So we need them to both work the same. And of course, that again is checking the phasing, and I'll show you how to do that here in just a moment. Since there are no markings on the speaker, I don't know which terminal is positive or negative on either speaker. So I need to figure that out. So I can very easily do that with a 9-volt battery, a current limiting resistor in line with positive, and all I'm going to do is just touch the leads and see whether the cone pulls in or pushes out. So if the cone pushes out, my red is positive and my black is negative. I'll know to mark the red side plus and the black side negative. If it pulls in, it would be opposite, so I'd have to reverse the leads. Now, if you're following along, you're doing so at your own risk. Doing a test like this takes common sense. You definitely don't want to be leaving the leads on the speaker for any long period of time because you're going to heat the voice coil up. So this is basically just tapping to see which way the cone moves. That's it. And again, I have a current limiting resistor. In this case, this is only 27 ohms, and that really does knock the movement of the speaker down quite a bit. So what I'm going to do is just attach one lead here, and I'm going to flip the speaker over. Hopefully I can get this on camera, and I'm just going to tap this one side here. So let's see what happens. Okay, so let's watch this. Now see whether it pushes out or pulls in. Okay, here we go. Just going to touch it. See, it's pulling in. So I know that I have the leads reversed. So I'll take the black lead off this side and touch this, and now it should push out. See it pushing out? Bad connection here, there we go. Pushing out. So I know this side is positive, right here. So what I'll do is I'll take my felt marker, because I have a black felt marker, I'll mark the negative side. Alright, so I'll just put negative here. Even the felt doesn't want to cooperate today. I guess I could just put plus here in black too, that's fine. There we go. So there we have it, so we know it. Now if we look at the colors on this speaker here, we have a green lead here and an orange lead here. So it pretty much tells us that this looks like this is most likely going to be wired correctly. So what I'll do is I'll just do the same thing with this. Even though the winding of the transformers across it, it should be okay. And I'll just touch this, and this one here should push out as well. Okay, so let's take a look. Yeah, it's moving. Probably not enough for you to see. So let me eliminate the current limiting resistor here. And I'll just quickly touch it, because we have a winding of a transformer and everything loading this down. See that? It's pushing out. So that is correct. So I know now when I put my transformer on here, if I hook my oscilloscope probe up the same way and I see both of the signals are in phase, we're doing okay. And if not, I'll have to reverse the leads, and I'll show you how to do that here in a moment as well. I've lightly cleaned the area with just water. I don't really want to use any chemicals around the speaker. It's in such nice condition. If anything drips down in there, it's going to cause an issue. So this is ink of some sort, and I could sit here and scrub all this off, but it's not really worth it. So I'll just leave that here, and I'll just clean the rest of the dust and debris off with a damp cloth here in just a little bit. It's not hurting anything, and it looks fine the way it is at any rate. Most of this stuff will end up being covered up with a transformer at any rate. So the very first thing I want to do is put a star washer on the screw that I'm going to use, and I have to insert this screw through the back side here. And the reason I have the star washer here is because I have no way to hold the head of the screw. So the star washer will bite into the screw and it'll stop it from spinning as I'm tightening the transformer down. Now all the hardware that I use in the amplifier and the hardware that I'm going to use here on the speaker is stainless. So these are stainless screws, these are stainless washers. The nuts that I use are all stainless. Everything is all stainless steel. That way down the road nothing corrodes and it's easy to get apart again. So all the tube sockets that you saw on the amplifier and everything that was mounted on that chassis is all stainless as well. So what I'm going to do is very carefully put my finger in here, push on the paper just a little bit, and I'm going to steer this through the hole like so. there it is. So I will put the transformer here, just like so. I'll put another star washer here, and I will thread this on here just loosely. Now that that's done, I want to do the other side. I want this to be nice and loose at this point. And what I'm going to do is I will put this through on this side here. Again, steering this around. I'll hold that just like so. Put that there. Put this up on here. And thread that on nice and carefully, just like that. Now all I have to do is just tighten this down, and we'll work on the phasing. Let's make sure that the phasing is correct. So I need to make sure that I'm going to hook these wires up correctly onto the speaker. So take your guess now. Do you think that this is going to directly connect to this and this, or do you think I'm going to have to cross these leads over? Again, we want to make sure that when this speaker is pushing, this one is pushing as well. We want them to work together, not against each other. Okay, so how I have this set up is I have the blue lead of this transformer attached to the blue lead of this transformer. You see the blue lead here, so there's a black lead running off to here, and the red lead of this transformer goes to the red wire up to the red lead of this transformer. I have my signal generator attached to the transformer. Doesn't matter which way I attach the signal generator, we just want to make sure that these are going to work the same. So I have my signal generator attached, and I have it set at a frequency somewhere around 400 cycles. Something that I can turn up on this end, and the mic isn't going to pick up so incredibly bad. Depending on what frequency you choose, it'll get pretty bad in the mic. So I tried to choose a frequency that's not so bad. So I get to hear it loud on my end, and you don't have to hear it so loud. So I've got the signal lead of my oscilloscope of this probe A, or trace A here, attached to this speaker here. So we're going to monitor this one, and we'll make this one match this one here. So you can see the signal lead is attached to the positive, and the common lead of my scope is attached to the negative of the speaker. The reason that this is a flat line and this is just noisy here is because this scope probe is open. We're not doing anything with it right now. This one here is across the winding of the transformer and the voice coil, and it's causing us to have just a flat line because it's basically taking the noise away. It's reducing the sensitivity, I guess you could say, of that channel right now because it's looking like a short to that channel. So what I'm going to do is I'm going to turn up my signal generator, and we'll take a look at what we see on trace A. So we're looking at this speaker right now. So here we go. Okay. So now what I want to do is I want to see if this is going to be the same. So you can see that this lead is connected to the signal lead of my scope. I want to make sure that this is the same. So I'll connect this up the same way as if this was going to be connected like this. All right, and let's see if it's going to be in phase or not. Place your bets. What do you think? Here we go. It's out of phase. So if I was to connect these up like this, as this one's pushing, this one would be pulling, and vice versa. Reason being is you can see when this one is on the down portion of the cycle, this one is on the up portion of the cycle. These should look the same in line, all right? So I'll give you an example of that. I'll reverse the leads here, so I'm going to have to cross these leads over. I kind of expected that because the winding is turned around on the core. All right, so here we go. Connect this up to this side, and this up to this side. And now, as you can see, when this one's on the down cycle, this is on the down cycle. As you can see, up over here and up over here. So these are in phase now. Because I repainted the reverb box, I had to remove all the innards, and that gives me a good chance to test these little windings out on each end here. Now, the reverb box was really rusty and wanted to freshen that up as well. So I'll just test this here. That's doing okay. And on this end, it's doing okay as well. So that's a good sign. The reverb will work. Here's the repainted reverb box. So as you can see, that cleaned up very nice. And I used a pretty tough enamel on this. The reason being is because you coil the cord up and you stick the cord inside the case. And a lot of the times the cord will hit this. and I don't want it to be taking the paint off. So this was surface prepped as well, so this was completely sandblasted. All the rust was taken off, and it's finished with a hammer tone style of paint. The underside is just primered, and the little bit of silver that you see is just overspray from the outside. Really doesn't matter because this is just inside the box, and the primer is on here just to stop any type of further corrosion or, any type of rust or anything like that. So this is ready to be put back together and placed back inside the amplifier case. The coupling caps have been changed, the noisy resistors are replaced, and all the components in the amplifier are verified. So really the only thing to do now is to see if signal's going to get from the input to the output. Now I already have the speakers mounted back in the box, so I just have load resistors attached to these leads that would attach to the transformer, and I'm just going to pick the signal off the output tube just to verify both amplifiers. Again, this single amplifier really is two separate amplifiers in one. So how this works is it's kind of an interesting setup. So you'll notice that there was a speaker with a larger magnet and then a speaker with a smaller magnet. And the one with a smaller magnet is the one that the audio transformer was replaced on. So the speaker with a larger magnet is attached to the instrument portion of the amplifier. So that's the clean channel. There is no reverb on that channel. What they've done is they've taken the signal from the speaker and they're driving the reverb tank right from the speaker. And the output of the reverb tank comes to the input of the second amplifier in here, and that's controlled by the intensity control. So one speaker is only clean. So you can turn that up and down, you can plug your instrument in, and you get lots of gain through that. And then the second channel is solely for reverb. So when you turn the intensity up, it's picking the signal off of the reverb tank. So it's allowing you to basically turn this speaker completely off and only use this one speaker for clean. And then when you want reverb, you turn that control and you just start to get reverb. So if you don't want reverb, you're only using one speaker. So one speaker is essentially off, and as soon as you give it any reverb, the other one is turned on with the other amp. It's a really bizarre setup, but it works, and it is unique, and I like unique things. So there you go. Neat little amplifier. So what we're going to do is test one section right now. Again, it's just into some load resistors. There's no audio transformers, so we'll see what happens here. So I'll turn the amp off of standby. And as you can see, one channel is working just fine, and this is the reverb channel. No problems there. And you can very comfortably drive this into distortion as well. So that's going into this input right here. So this is the output of the reverb tank going into this input here. So now what I want to do is I'll turn that on a standby. So I want to move this to the other output tube. So this is the clean channel. Just put that right there. And in order to try that, I have to attach it to one of the input jacks here. This is just the clean. In fact, I can just clip it right to that resistor right there. That'll work just fine. So I'll turn this on and give it some gain. And it looks really nice. So both channels are working just fine. The amplifier is back in its case and all the wires are reattached to the transformer. I used some really nice heat shrink tubing on the wires. It's really thick and it has an adhesive inside. So made a really nice job there. Everything is reattached. So we're ready to put some sound into this thing. Or tone at least. We'll vary the tone a little bit. Plug that in there. I don't know where my audio generator is sitting, but we'll find out pretty soon. Attach this to here. So I'm just putting a signal in channel 1 right now. Make sure everything is down. It's on standby. Let's turn it on. And there we go. So wait for the tubes to warm up. You can see the filaments start to glow here. So a few more moments, and I'll flip the switch and we'll try this out. All right, here we go. That's nice. The hum level is extremely low. It's a nice silent amplifier. Okay, so intensity is down because this is the reverb. So the tone control really isn't going to do much here because we're going to just be putting a single tone through. Nice and clean. That's this speaker right here. All right, I'll turn the reverb right up. Oh, I can hear it echoing already. That works really well. All right. Let's make some sci-fi noises. And it can be driven into overdrive real nice. It's working great. Again, no reverb. Very nice. Project successful. All right, so now all I have to do is put this back on and it is finished. That turned out really well. I'm very happy with this project. If you're interested in learning more about electronics and gaining access to many of my personal inventions and designs, for example, those little custom pieces of test equipment that you've seen throughout this video, you're definitely going to want to check out my ongoing electronics course on Patreon. There's many videos up there as well. I'll put the link just below the video's description under the Show More tab, and I'll also pin the link at the top of the comments section. So if you click on the link, it'll take you right there. If you're enjoying these videos, you can let me know by giving me a big thumbs up and hang around. There'll be many more videos like this coming in the future. We'll be taking a look at vacuum tube and solid state electronic devices alike. So if you haven't subscribed, now would be a good time to do that as well. I have lots of really interesting videos planned. I'm just getting started. Until next time, take care. Bye for now.